Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 7 on the distance formula. Now, the distance between 2 points in a coordinate plane is one of the most important measurements that we make in the coordinate plane. So we want to have a way to find that distance very easily and very formally, and that's what we're going to be taking a look at today. So let's get into the distance formula. Now you're probably going to want a calculator. I just have a nice little scientific calculator going on here that I'm going to bring out when I need it. All right, make sure that you either have your graphing calculator handy or sort of a scientific calculator. Now let's talk about finding distances in the coordinate plane. In our last lesson on the Pythagorean theorem, we saw that we could use it to find the length of a line segment. This is also the same as finding the distance between 2 points. And again, I can't emphasize that enough. The distance between point A and point B in the coordinate plane is exactly the same as finding the length of line segment AB. If not, then we have to really get back into what distance and length are. So let's get into exercise 1 and review how to use the Pythagorean theorem to find that length. A segment is shown below with endpoints at A, 2, 3, and B, 14, 12. Letter A. Draw a right triangle on the grid that has horizontal and vertical legs and that has AB as its hypotenuse. Reproduce it below with the lengths of its legs labeled. All right, let's do this together. The idea here is that any line segment that's in the coordinate plane that's slanted can become the hypotenuse of a right triangle by just drawing in a vertical and a horizontal leg. Right, let me draw in that right angle symbol just like that. Okay? Now, I would like to reproduce that right here just so that I can get a better picture of that right triangle. So what does that look like? All right, it looks something like this. All right, with this point being A and this point being B. All right, and because the legs are horizontal and vertical, I can figure out how long they are. So what do I have? I've got 8, another 4 is 12, so that's got a length of 12 there. And then I've got 5, 7, 8, 9, and so I've got 9 there, right? And I can do that simply by counting how long that is and counting how long that is. Now let's talk about letter B. Determine the length of AB, or the distance between A and B, using the Pythagorean theorem. Show your calculations. All right, well, we've reviewed the Pythagorean theorem now. I'd like you to take a moment and figure out the length of AB using the Pythagorean theorem. Now, AB happens to be the hypotenuse in this case. All right, so it's C, if you will. All right. Whereas the 12 and the 9, there are A and B. So I can say, as always, A squared plus B squared equals C squared. But my C now is what I'm looking for, right? So I'm going to say 12 squared plus 9 squared. And I'm going to use AB as the length of AB because, well, that's what it is, right? So I've now got 12 squared, which is 144. 9 squared, which is 81, and that's going to, and that's not going to be plus, but that's going to be equal to AB quantity squared. If needed, bring your calculator out at any point in time that you need to. Just, you don't want to botch calculations just because you didn't take that out. So AB squared is going to be 225. Take the square root of both sides, and AB is going to be 15. Again, if you don't know that the square root of 225 is 15, grab that calculator. All right, let's try to put our calculator back away. All right, now, importantly, right, when I figured out the 12 and the 9, I did it by looking at this picture and going, well, I got 3 plus 5 is 8, plus another 4 is 12, and then here I have 2 plus 5 is 7, plus another 2 is 9, right? I literally counted boxes, right? We don't want to have to do that. So let me bring it back down here, right? Remember, we had this was 12 and this was 9, and this was point A and this was point B, right? We want to be able to figure that 12 and 9 out without, having to count. So let's take a look at letter C. How could we have found the lengths of the legs using the coordinates of the endpoints? Illustrate below. So I'd like you to look at these two coordinate points and the 12 and the 9, right? And I want you to think about how we could have come up with the 12 and the 9 without ever having to count boxes or anything like that. Well, we can do it by subtraction, all right? So in other words, if we look at these two x coordinates, right, the change in x, which is the distance between them, 14 minus 2, is 12, right? That's right here. And if we look at the two y coordinates, 12 and 3, the change in y, 12 minus 3, that's equal to 9. So in other words, we can figure out the lengths of the legs by subtracting the x coordinates and subtracting the y coordinates. Subtraction always gives you distance, assuming that the answer is positive. And the answer is not positive, you take the absolute value, and that will then make it positive, okay? So, where does this lead us? Well, let's see if we can use this without even having a coordinate grid. Let's take a look at exercise number 2. Find the distance between the points 2, 5 and 6, 13 in simplest radical form. Draw a right triangle to justify your approach. Okay, pause the video now and see how much you understood about both that subtraction idea and using the Pythagorean theorem in order to find distance. All right, well, let me just draw a little bit of a right triangle. Right? I don't need to draw it to scale or anything like that. Just, I've got my right triangle, right? And at one point, down here maybe, I've got the point 2, 5. And the other point, let's say up here, is 6, 13. Now, the horizontal distance between those 2 points, which is this, is given by 6 minus 2. So that's going to be a length of 4 right here, right? That's just 6 minus 2. And the vertical distance between the 2 points, that's given by 13 minus 5, right, which is given by 8, right? So this is 13 minus 5, and this is 6 minus 2, right? The change in x gives us the horizontal distance between the 2 points. The change in y gives us the vertical distance. But now we can figure out the length of the hypotenuse, right, which is what we're looking for, that distance, by just saying 4 squared plus 8 squared is equal to c squared. 16 plus 64 is equal to c squared. 80 is equal to c squared. I wish 80 was a nice perfect square. It's not. So I get c equals the square root of 80. I would love for you to be able to finish just at that point. But this particular problem asks us for the answer in simplest radical form. Now remember from our last lesson on the Pythagorean theorem, the way that we write something in simplest radical form is we try to figure out what the largest one of these perfect squares is that goes into the number 80, right? Now 4 goes into 80, it goes in there 20 times. Unfortunately, 4 is not the largest perfect square that goes into 80. And now, by the way, if you're not sure what the largest perfect square is, there is absolutely nothing that prevents you from sitting here and going, oh, let me look at 80 divided by 4. Well, okay, 4 goes in there 20 times. Let me do 80 divided by 9, right? And nope, that's a decimal, so that's not it. How about 80 divided by 16? Let me see about that. Oh, that goes in 5 times. So 80 divided by 16, 16 is a factor of 80, and in fact it goes in 5 times, so c is the square root of 16 times the square root of 5, and c is 4 root 5. Now again, none of what we just did from that step down to that step has anything to do with distance or the Pythagorean theorem or anything like that. It's simply how do you write a square root in its simplest form. We could totally debate whether or not 4 times root 5 is simpler than the square root of 80, but unfortunately we just got to know how to do it. So now what we want to do is we want to generalize. We want to come up with a formula called the distance formula that will allow us to just basically plug and chug. So let's figure out what that formula is in exercise number 3. Given 2 arbitrary points in the xy plane, x1, y1, and x2, y2, determine a formula that can be used to find the distances between them based on the Pythagorean theorem. All right, well, let's do this together. Exactly what we did in the last problem, we can now say that this particular length is simply x2 minus x1. And I'm going to put it in parentheses. We'll understand why that is in a little bit. Right, that distance, whatever it is this x-coordinate minus this x-coordinate. And the vertical distance, this one, is simply y2 minus y1, again in parentheses. The actual distance or length that I want is the length of that hypotenuse. I'm going to call it c, right? So my a, let's say, is equal to a x2 minus x1. Let's say our b in the Pythagorean theorem is y2 minus y1, right? Our Pythagorean theorem now says a squared plus b squared is equal to c squared. A is x2 minus x1. B is y2 minus y1. And c is just c, right? So now if I were to solve that for c, by just taking the square root of both sides, I could now say that c, or the distance, is simply equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Now, never forget, because we're going to work with this formula a lot, that formula is simply the Pythagorean theorem. That's it, right? Where this is your a squared, this is your b squared, you add them together, and then you take the square root to find the length of the hypotenuse. Now, in the Pythagorean theorem, we oftentimes just have it as, obviously c squared equals a squared plus b squared, but here we're already putting the square root in so that we can literally just take our endpoints and plug them into this formula and come up with that length or distance. So let's formally introduce it now, the distance formula. If x1, y1 and x2, y2 are 2 points in the plane, then the distance d between them can be found by d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. So again, exactly what we just saw. All right, I don't want you to think that this is some kind of crazy complicated formula. We got a, x2 minus x1, we got b, y2 minus y1. We find those two differences, we square them. One nice thing about squaring, any number is that it turns the result positive, right? So regardless whether x2 minus x1 is positive or negative, once you square it, it's positive. Likewise here, once we square that difference, it'll be positive. We'll add those two positive numbers together, take their square root, and we'll have the distance between those 2 points in the coordinate plane. All right, let's actually do a little bit of this. Exercise number 4. Find the distance between each set of points shown below using the distance formula. All right, great. So here we go. I am going to literally just sort of plug and chug. I'm going to say my distance is equal to the square root of x2 minus x1 squared, that's just that horizontal distance, and I'm squaring it, y2 minus y1 squared. All right, I like to take my time here. 15 minus 3 is 12. 7 minus 12 is negative 5. But again, that's not a problem because we're going to square it, okay? So yeah, that's negative, but we're going to square it. Notice how I'm keeping both of those in parentheses, right? Now, 12 squared is 144. Negative 5 squared is positive 25. 144 plus 25 is 169. And my last piece is the square root of 69, 169, which is 13. So the distance between these 2 points, without having to draw it out on a coordinate grid or anything like that, throwing down a right triangle, none of that, the distance is 13. I'd like you to pause the video now and see if you can do the same thing here. Watch your positives and negatives. We're going to have a 5 minus a negative 3. You got to watch out for that. That can be a little tricky. Pause the video now and see what you get. All right, let's do it. Plug and chug. Okay, we've got the distance equals the square root of 5 minus negative 3 squared plus 10 minus 4 squared. Now don't forget, when we do that subtraction of the x-coordinates, we're looking for the distance from this x-coordinate to this one, right? The major mistake that a student would make here is that they would just do 5 minus 3. But that would be weird. That would say that the distance between negative 3 and 5 is only 2 units, right? But in fact, if I were to go from negative 3 to 5 on the coordinate grid, that would be an 8-unit distance. An 8-unit horizontal distance is separating those two x-coordinates. So never forget that. Likewise, right, the distance from 4 to 10 is 6 units. Now it's just kind of finishing this thing off. 8 squared is 64. 6 squared is 36. 64 plus 36 is 100. I love the square root of 100. It's a nice number. That distance just ends up being 10. Okay, so it's easy, right? Subtract the x's, find the distance between them, square it. Subtract the y's, find the distance between them, square it. Add those two squared distances together, and then take the square root. And that's your distance formula. It is just the Pythagorean theorem, though. Okay, so if you like the Pythagorean theorem, if you're good at the Pythagorean theorem, the distance formula should be good for you as well. Now, just like our work with the Pythagorean theorem, the distance formula can result in lengths that are irrational numbers. And whenever you've got something like that, so in the last problem, they turned out both to be nice. But when you've got those lengths that are irrational numbers, then either you're going to have to put your answer in simplest radical form, or you're going to have to evaluate it in terms of a decimal, typically. Let's take a look at what we're going to do in exercise number 5. Find the distance between each set of points shown below using the distance formula. Express each answer in simplest radical form. All right, so there's our simplest radical form again. All right, let's do the first one together, then we'll have you do letter B on your own. Here we go. So I'm finding the distance between the points 4, 1 and negative 2, 10. All right, so I'll do the square root of negative 2 minus 4, so x2 minus x1 squared, plus y2 minus y1 squared. All right, now again, need to be careful. Negative 2 minus 4 is negative 6, right? The distance between them is 6 units. 10 minus 1, that's simple, that's just 9. All right, negative 6 squared is, of course, positive 36. 9 squared is positive 81. And when I add those together, I'm going to get 117 under the square root. Now I've got to simplify this perfect square. And yet again, right, the idea is I'm looking for the biggest one of these numbers, right, that goes into that particular radicand, right? So I'm thinking about 117. Now 117 is not even, so 4, 16, 36, 64, those are all out. There's no way if that is an odd number that I'm going to get an even number to go in. But, you know, I could try 9. I could see if 9 goes in there. So there's always that chance. And if you're not sure, of course, all you have to do is just type in 117 divided by 9 and see if 9 goes in there. And in fact, it does, right? 117 divided by 9 is 13. Now, how am I confident right now, though, that that is the biggest perfect square? Well, when I look at what else remains, the other factor, 13, I simply have to ask, are there any perfect squares that divide into 13 other than the number 1, because it divides into everything? And the answer is no, right? 13 is a prime number, and so I'm done, right? That's as good as I can get. So I can now say this is equal to the square root of 9 times the square root of 13, which then is 3 times the square root of 13. All right. Again, it's unfortunate that we have to spend any time simplifying these radicals, but you want to get every point you can on a particular test, so we got to do what we have to do. All right. Why don't you go ahead and pause the video now and see if you can find the distance between negative 2, negative 5 and 8, 0 in simplest radical form. Again, watch out for your subtraction. You're going to be subtracting some negatives here, and that can always throw some confusion into the mix. All right, let's go through it. Put a little dividing line right here. Maybe move this thing over. My distance is going to be the square root of 8 minus negative 2 squared plus 0 minus negative 5 squared. All right, the distance between 8 and negative 2 is 10, right? That's 10 units. And 0 minus negative 5 is positive 5 units. So now we're going to have the square root of 100 plus 25, which is, last time I checked, the square root of 125. Now this one, I think, unlike the last one, is not going to be too hard to figure out which one of these perfect squares divides into 125. I'm hoping it's pretty obvious that it's 25, right? In fact, 25 fits into 125 5 times. There's a lot of 5s going on here. So my distance is 5 times the square root of 5. Okay, right? Lots of Pythagorean theorem, right? Or distance formula, whichever one you want to call it. Let's take a look at one last problem. All right. Now we will often use the distance formula to determine the length of sides of figures drawn in the coordinate plane. That will be our main use of this particular formula, is to just simply figure out how long is a given side of a figure in the coordinate plane. Now let's take a look at a consideration in exercise number 6. Triangle ABC is shown below with vertices at A, negative 3, 9, B, negative 2, negative 3, and C, 6, 1. We would like to determine if triangle ABC is isosceles. Letter A, which two sides appear to be the same length? Appear. All right, this should be simple enough. Pause the video now and write down which two sides that you think could possibly be the same length. All right, well, there's no question that no matter how long the three sides are, BC is the shortest side, right? So if we have any hope for this being isosceles, it's AB and AC that could be the same length. Now again, maybe they're really close, right? And just not quite the same length, right? That's where letter B comes in. Use the distance formula to see if triangle ABC is isosceles. Now, we could totally find the length of every one of the three sides, no question about it. But given that we've got the graph here, and we know that there's no possibility that BC could be the same length as AB or AC, all I really need to do is check to see if these two have the same length. So first things first, let's figure out what the length of AB is, all right? And I'm going to actually write it down like this. AB is equal to, right? Now I'm going to use the distance formula because literally that's what I'm doing here. I'm finding the distance between point A and point B. So I'm going to have negative 2 minus negative 3 squared, right? Then I'm going to have negative 3 minus 9 squared. I just have to be very careful with all my signs. Take my time. Negative 2 minus negative 3 is positive 1. Negative 3 minus 9 is negative 12. Right? Of course, all those negatives are going to go away once I square them. I'll leave myself some room here. 1 squared is 1, and 12 squared is 144. So I'm going to find that the length of AB is the square root of 145. Now notice in this problem they didn't say anything like use the distance formula to determine if ABC is isosceles, and by the way, round to the nearest blank, or write in simplest radical form, or whatever. So for right now, I'm going to actually just leave my answer as AB equals the square root of 145, right? The square root of 145 is a number, okay? Whatever that number is, it's sitting right there, okay? I don't need to take this any further. At least I don't think I do, right? So let's now figure out the length of AC. Pause the video now and use the distance formula. Let me erase this and be very clear. I now want to find the distance formula between this coordinate point and that coordinate point. So pause the video now, take a few minutes and carefully find the distance or the length between those 2 points. All right, well, let me start it right here so that it's still sort of on the screen. I'm going to put it right here. So AC equals the square root. All right, so I'm going to call this my x2 and my x1. So I'm going to have 6 minus negative 3 squared plus 1 minus 9 squared. All right, now I can kind of move this up out of the way a little bit because I don't need those points anymore. All right, again, careful. 6 minus negative 3 is 9 squared. 1 minus 9 is negative 8 squared. All right, 9 squared is 81. Negative 8 squared is 64. And if I add those two together, 81 and 64 is 145. So AC is the square root of 145. And here's the beautiful thing. Right now, without simplifying any radicals or coming up with any decimals or anything like that, I can see that AB and AC are the same length, right? They both have a length of square root of 145. So ultimately, use the distance formula to see if this is isosceles, and the answer is yes, it is. Maybe don't put a period there, because AB is equal to AC. Or you could say yes it is, because AB, the segment, is congruent to AC, the segment. All right? And this will be a very common thing that we're going to be doing with the distance formula. We're going to be using it to see if two side lengths of a particular figure have the same length. All right, let's summarize. Now, we all know that the Pythagorean theorem is one of the most famous formulas in all of math, but the distance formula is as well, and it gets used a ton in coordinate geometry work, especially in the course that we're in right now. Now, what I never want you to forget, though, is that the distance formula is the Pythagorean theorem just in the coordinate plane, where you're always finding the length of the horizontal leg and the length of the vertical leg of a particular triangle by simply subtracting the x-coordinates of the 2 points, subtracting the y-coordinates of the 2 points. Those are giving you those lengths. You then square them, because that's what you do in the Pythagorean theorem. Add them together, again, because of what you do in the Pythagorean theorem, and then take the square root to find the length of the hypotenuse. And that's one of the cool things about the distance formula. Unlike the Pythagorean theorem, which could be used to find the length of either one of the two legs or the hypotenuse, in the distance formula, you're always finding the length of the hypotenuse. Always. All right, well, we'll get a lot of work with the distance formula as we move through the rest of this unit and through the rest of the course. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.